don't know what my pen is doing, but anyway, as long as it's writing. We kind of say that we will want to open this like this, right?
Yeah.
It's either ring opening or ring closing, it doesn't matter. I'll call this ME, I'll call this CH3. Actually, the bottom one, let me make it dash dash. So we say that if you are going with a number that can divide by 4, you're going to be disallowed thermal. I repeat, if you're going with a number that is divisible by 4, is that an English word, divisible?
Divisible, yeah.
Oh, okay. Sometimes I confuse myself. If you go, so this is the thing, Jada. Anytime you have an arrow, that is 2 electrons, right?
Yeah.
So if I have 2 arrows, then I'm involving 4 electrons.
Okay.
So if that counts to a number that can be divided by 4 with no remainder, and I'm heating, it's thermally disallowed, which means if I have dash dash on here, if there was any way to do stereochemistry, then I would say it should go anti. But remember, I called this out. What did these were the out groups, right?
Okay.
So those ones are supposed to be opposite like this. Instead of down here, you see how these are opposite?
Yeah.
We do the same thing here. They will face the same side. Maybe like this. Or like this. Depends on which side you're rotating. Because this is in, this is out. This one here is photo allowed because the number is divisible by 4.
Okay.
So you keep, oh wait, these are opposites, right? So it's not supposed to be like this. It's supposed to stay the way it was originally. It's gonna go in. So whatever you see is whatever stays. You'll understand what I mean. It's gonna come back to you. Just follow me closely. I don't want to go into the Obiro drawing of Obiros. I'll lose you so much if I do that.
Yeah. I was like looking at the textbook and I was like, oh my god, when is the orbital stuff happening?
So here we're going to just say stereochemistry is kept. That is what we mean by allowed. Disallowed, that means that stereo chemistry is switched. So if you have C's, it goes anti. In this case, C's to anti.
Okay.
This one is gonna stay anti. Why?
Okay.
Because the condition is 4, and we have a number that can be divided by a number of pi electrons that can be divided by 4, and they stay.
Okay. Got it.
Good?
I remember it, but I was just like confusing myself.
Yeah. Let's do a couple more.
Okay.
It gets to a point you will talk, I will not talk.
There's so much I have to like rememorize. I don't know how I'm gonna do it.
I'm trying to come up with something. I think this will work. These are the coup rearrangements, you could say, but it's more. This is just the space is not gonna stay, so it's kind of a sigmatropic arrangement.
I got the like Copic plays and stuff like mastered today.
Good. So let him not make a mistake. You'll be smiling.
I'm scared.
I told you not to be. Please do not, for my own sakes. It's a hard thing to ask, but try. So the arrow is going between 2 and 3. Between 1 and 6. And between 4 and 5. Right?
Do the rules change because there's 6 pi electrons?
Now you decide, yeah. So is it gonna be thermally allowed or disallowed, this one?
I think this one's allowed.
Thank
I know
you.
it's like the opposite of 4.
Thank you. Because you're involving 6 pi electrons. 3 arrows. There's a harder way, there's a harder way to explain this. I don't want to go there.
Yeah.
We have other things to talk about. Now, suppose someone gave you these ones like this on 1 and 6. Then you will want to show the metal groups seen.
Okay.
Yeah. Or the other one. I know. Chemistry is just a mess. But it is what it is. What do you do?
Okay.
Do the same molecule, and this time you're going to do HV. And I know you're gonna tell me this is photo disallowed. Yes, cyclization will happen, but
Like outside groups are going to be different.
correct. Because someone is gonna go conrotatory on this one. This rotatory, I think, goes with the ones that were allowed. Conrotatory goes with the ones that are disallowed.
I don't know what I was so confused over. I was like really, I had to like move on. I was so confused.
You just had forgotten the reasoning behind it, but that's the reasoning. Now I'll have you do this one. Just this one. On HB.
So is it?
Then you describe to me what you get.
What like is the out and what's the in? Like, is one preferred to be a wedge and one's preferred to be a dash?
No, that's why we draw two products. As long as you end up opposites.
Okay. I just did dash wedge.
Yeah, that's fine.
Okay. So it's not like an in is a wedge and an out is a dash.
Normally I take my out to be the wedge, I believe, if I remember correctly. And then I take my in to be the dash. But really, you can tell that it doesn't matter because it depends on which carbon you're rotating, carbon 1 or carbon 6.
Okay.
Which is why we just draw. I know one of those should be in out, but it really doesn't matter because the outcome, let's see, there should be a double bond here, there should be a double bond here. Yeah. 1, 2, there should be a double bond here. And 4, 5. How did I draw my 5-member doing? Anyway. Okay. Anyway, you get the idea. So, since you always end up with both, it doesn't matter. Okay. What was the other thing again?
The homotopic, heterotopic, aneotopic, diastereotopic.
Yay! You really want to go back there, but you never know.
I didn't do good on, like, there were 4 of them on my exam, and I got 1 right.
In organic 1, organic 2.
Organic 2, like, it was my exam 3. It came from chapter 15. It was like, to help determine, like, splitting patterns in H&MR.
Yeah, because they will ask you how many signals, and that's what's gonna help you. So now let me give
Can we
you.
go over that too, like looking at a molecule and trying to figure out how many signals there are?
Of course, that's what we're going to do. Once you determine whether they are homotopic, that's your topic, whatever it is, then we determine.
Okay.
Remember, enantiotopic hydrogens are usually chemically equivalent, but I'll explain that.
Okay. I don't know why this never like stuck. I had a really hard time with this.
No problem. I'm here to help you. And you have no choice but to understand. That's always my goal. The student must have no choice but to understand. So I'm drawing those hydrogens. I'll wait for you to draw. I'm drawing those hydrogens with colors because because I like coloring anyway. I like drawing, I like painting, I like coloring. But here, just for identification of what you're doing here. Now, if you look at the red, if you take the red, what's happening into my laptop? I know I've overused it today. If you take the red and replace it with whatever, which is where I remember last time it got confusing. You replace your red with a Cl. I would have used beer, but I already have a beer. And then do the same thing for the green one. Can you see my drawing?
Yeah.
Okay. So we replace the green one with the Cl. This time we keep the red. What is the relationship between the outcome?
Is this enantiomers? They're just like flipped?
No, they're diastereomers because one position is kept and the other one is switched. So I believe that's one of the problems, definitions.
Wait, can we go over the definitions?
Diastereomers are two molecules that have the same atom connectivity with at least 2 chiral centers, a carbon with 4 different things. The chirality of one position is kept, at least chirality of one chiral center is kept, at least chirality of the other chiral center is switched. Enantiomers, both of them will flip. You see how the Br stayed a wedge?
Yeah.
That's why. So this is kept.
Switch.
Yeah, that's kept. These ones are switched.
So enantiomers are there still 4 different things bonded?
Enantiomers are stereoisomers, so it has to have chiral carbons. The ones, well, we don't even need to go there. Enantiomers and diastereomers must have chirocarbons.
Okay. And then
Enantiomers, everything will be flipped.
okay.
I will show you an example.
Okay.
So I've showed,
Right. And then when we're done with like your examples, can I show you my exam so that we can look at that so I can understand why I got them wrong?
Yeah. So those two hydrogens are diastereotopic. Now, take these two hydrogens now. Okay. Black insisted, black is used. We do the same thing. So I should have drawn it up here. So replace this with a Cl, for example. Then do the same thing. Keep the black. Replace the red with the Cl. And then compare the outcome. This is always the process.
So is this diastereotopic?
No.
Oh my god. I don't understand.
Me too, I don't understand why you don't understand.
Why is it?
What is the relationship between those two molecules? There's
Well,
only one chiral center. It cannot be di. For diastereomers, you have to have at least, you can have an enantiomers with multiple chiral centers, but diastereomers, you must have at least two. Enantiomers does not need two chiral centers. It can be just one. This one right here, I'll tell you that you're going this way. The smallest group is on the back. This is R, and that's S. So the chirality has been switched. These are enantiomers, and therefore these hydrogens are enantiotopic. Like I said again, the main problem here is your definitions.
Okay.
I repeat, diastereomers must have at least two chiral centers. At least one chiral center is kept. At least one chiral center is switched. The chirality, that is.
What if both were switched?
Then you have enantiomer only and only if there is no internal plane of symmetry. Then they will become meso.
Okay. And then what's like homotopic and heterotopic? What's that?
I don't think there's heterotopic. Is there?
My professor said there was. Like,
I think diastereotopic hydrogens would be called heterotopic because they see different things in space. These are homotopic. These two hydrogens will show up at the same place. Why? Because they see the same thing. They see hydrogens on the neighboring side. This red is seeing the bromine. This green is seeing the hydrogen. They are seeing different things topically. So we say topic on top. So those two hydrogens should be diastereotopic. But let me make sure that diastereotopic is not under heterotopic or is under heterotopic. So they are saying those two are different, but let me find an example. But you understood what an antiotopic is, right?
Yeah.
Now I'm going to narrow. I think heterotopic is being explained here that it comes from constitution isomers. Let me check. Then I'll have a clear. So homotopic hydrogens are chemically equivalent, and these enantiotopic hydrogens here will show up on the same chemical shift. If the hydrogens will have the same chemical shift and give you one signal, then we say that they are homotopic. That's the definition for homotopic. So homotopic, the pair of hydrogen will show up on the same chemical shift.
Okay.
They're stereotopic. Those are different signals. For example, here, if I have to say how many signals I have for the first molecule, it's gonna be from the CH3 as 1. Then the hydrogen, the black hydrogen, will be 2. Then the red and green will be 3 and 4. And then you have a CH3, 5. So I'll expect 5 signals in the first molecule because they are all chemically different. The diastereotopic hydrogens give their own signals. That's what I'm saying. So you count them as 1. Enantiotopic hydrogens, you group them. Can you hear me? I'm cutting out.
No, yeah, I can hear you.
Yeah, so how many signals do you expect in the second molecule?
The enantiotopic one?
Yeah, how many signals overall in that molecule?
3.
No, they're just 2. Those 2 CH2s are the same.
So the CH3s are the same too?
Yeah.
Okay.
Oh, so there are 2. Yeah, they're just 2. That molecule can have symmetry. If you just push the top CH3 down, you'll have internal plane of symmetry. Then it becomes only 2 signals.
Okay.
There is one more case scenario. What if neither a plane or axis of symmetry reflects 2 protons and they are not still chemically related? In this case, they are still chemically not equivalent, but specifically, these are constitutional. Yeah, okay. So this is a unique one. These are just constitutionally different heterotopic protons. For example, replacing the following 2 protons with another group gives 2 constitutional isomers. I'm gonna draw it to you.
Okay.
For you. So when there is no stereochemistry whatsoever, then you know that you have heterotopic. Let me see if my pen will behave. What can't I write? Let me see. I'm going to come back to join in, okay?
Okay.
Well, technology. Technology can sometimes be a headache. Anyway, I mentioned that what I read in mastering chemistry, they are saying heterotopic hydrogens are rare. It's a rare concept, but this is what it is. It made sense to me. So suppose you have these 2 hydrogens. they are obviously going to have different chemical shift, right? Obviously, we don't need to test them. That's what the article is saying. That's why it's rare to be heard. I was wondering why have I not heard of it? Maybe when we were studying last time I reviewed and forgot. So replace the hydrogen with chlorine and the red hydrogen, then the black, keep it. Do the same for the black one. Replace it with the chlorine and then keep the other one. What is the relationship between these two molecules?
They're different?
I know they are different, but they are constitutional isomers. Same molecular formula, different drawing.
Okay.
So anytime you replace two hydrogens and you get constitutional isomers, then those hydrogens are said to be heterotropic.
Okay.
Okay? Anytime you replace two hydrogens with an element, deuterium or chlorine like I do, and you get constitutional isomers, then you know those hydrogens are really heterotropic. So another example is here, this one. So let's say you're looking at that hydrogen versus this hydrogen, and you draw your two molecules. You go chlorine there, keep the hydrogen, keep this hydrogen here, and then here you go chlorine. These are constitutional isomers. So this hydrogen and that hydrogen, they are heterotropic.
So it's different chemical formula, or
No.
same chemical formula, different drawing.
Correct.
So I don't take naming into consideration, because I think that's where I went wrong on my exam. I was like, they have different names.
Oh, they will have different. The outcome has different names for sure, and that's how you know. They have to have different names, but the same number of elements, same number of carbons, hydrogens, oxygen, whatever. That is what defines constitutional. Constitutional isomers are molecules that have the same formula but different names, if you will.
Okay, got it.
So your reasoning was just in line, only that I don't know what you're comparing, because you have to keep the original and draw two more. That's what I've been doing. I'm keeping my originals and then I draw two more.
Can I show you my exam?
Go ahead.
Because I'm using that same knowledge on this one problem that I'm looking at right now, and he marked it wrong. I feel like
Let me see. Show it to me. Because then that would be weird, because that's the definition here. Heterotropic protons, replacing the two protons with another group gives two constitutional isomers, which is why they are called constitutionally heterotropic.
Yeah. So this was the exam, and I only got this one right. I only got this diastereotopic.
That is the stereotopic, the first one. It's kind of what I did actually, but with a beer.
Yeah, this makes sense. I understand that. I said this one was heterotopic.
Which one?
This one that says homo.
That one, you said that one is heterotopic, that is homo. They're on the same carbon.
But isn't that what you just did and it was hetero?
No. They're on the same carbon, my friend. Those two hydrogens are on the same carbon. Are they on different carbons?
What did you say?
Are those two hydrogens on different carbons?
No, so that's where I went wrong.
Yes. So if you are looking at that one hydrogen that is going up, and then you move to the next carbon down and put a hydrogen there, and then you replace the groups, then they become constitutional isomers. Right now, they are sitting on the same carbon.
So this would even have the same name.
They will have the same name.
So then, this one I said homotopic.
That one should be because there's a plane of... Oh no, that one is not, because you have a chiral center. You see that methyl group right there?
Mm-hmm.
That's a Cairo center once you replace the
This is a
hydrogen.
chiral center, or the
It's
hydrogen
not
center?
yet a Cairo center until you put a group on those hydrogens.
So it'll form if I put another. So if I do a Cl here.
Do this and
Yes.
share. And share, I show you. Because English.
I remember trying to do this on my exam, and it took me like 15 minutes. This makes a lot more sense now, but.
Am I sharing?
No, not yet.
I think the goal is for you to see why. That's the goal. Regardless of what you're thinking at that time, at the moment. So this is my original. Forget about the original. Draw two more. The moment I put a chlorine here, right now this is a chiral because there's internal planar symmetry. It's not chiral because going this way is the same as going that way. But the moment you put a chlorine, it becomes chiral, which is which is why now you can pretend that, okay, let me pretend but that my metal group is away, and then just be consistent with what you've decided here. Put the metal group away and then put a chlorine here. These two are diastereomers.
Because there's two chiral carbons and only one changes.
Thank you.
I think I said homotopic because I saw that there was a plane of symmetry, and I was like, okay.
So the problem here is this: your professor hid he hid this information. If this was a wedge, trust me, you'll get it right. But it was not defined. You're supposed to define it yourself. That was the trick.
Okay. And then I'll share again so I can show you the next one because I got that wrong too. I did really bad on this.
It's okay, bye.
I did good on the exam, but I didn't. I said an anti-topic for this one.
Those ones are stereotopic again. I'll show you why. Again, he caught you on not defining what the OH is. Yes, same catch.
Yeah, I'm sure.
Can you see my screen?
Yeah, sorry, I couldn't stop sharing. I was like, how do I do this?
Okay, so you have an OH, a butterfly. This molecule, original molecule, is a chiral. But if you're investigating these two hydrogens, then just pretend that your OH is a wedge, because it's gonna turn chiral the moment you put something here. It's gonna turn chiral.
Okay.
So that versus
that makes sense.
These are diastereomers.
In case of the two chiral carbons, one changes, one doesn't.
Thank you. Definition. So these two hydrogens of the original becomes diastereotopic because putting something one at a time where they are, you get diastereomers.
Okay.
And this is how you study. That's what I was saying. When you get a chance, when we are a week behind before the exam, or no, 2 weeks before the exam or 3, start with the exams. See where you went wrong, because those are the ones likely to come bite you.
Yeah, I've been like going over the material and then like taking the exam as if it's an exam, and then like looking to see if I got that wrong. And this was the only thing I like did bad on.
So now you're good?
Yeah. Oh wait, yeah, and then there was a question about how many signals.
Oh, how many signals? Okay, so on the first one, obviously I would show my hydrogens now, all of them, because they are stereotopic. They would stand alone.
They're all gonna have their own.
Yeah, but the thing is there's gonna be, because the molecule is symmetrical.
We're gonna have doublets, like two.
No, I'm just saying this and this will be by themselves. They'll show up at the same signal. Let's pretend that this was a wedge, for example. then the blacks will see the OH on the same side. And then this and this will be by itself. And then we have the CH3 and the CH3. Obviously, there's extreme symmetry for these CH3s. This will be by themselves. And then there's a hydrogen here. So A, B, C. This will be by itself. Because actually B and B will be seeing this hydrogen, D. And then E. Am I seeing 5 signals here? If I'm to count them correctly based on the rules, I see 5 signals. What was the key saying?
Transformers have all like separate signals.
Yeah, so how many signals? Or you were not asked about the total signals in the exam?
He like gave us a molecule and then they were labeled like A, B, C, D. And we just had to say like if it's a doublet, a triplet.
Okay, so the number of signals here are 5, but Cher, let me see the molecule.
I got this right, but like now that I'm looking at it, I'm like, I don't know.
You don't remember how you got it right.
It's like I remember it, but this one where I got on it, I'm just like trying to count it. Like, I understand why A is a doublet. And then B, because I thought it was things that are directly attached.
B, but you have a CH2 on C, so those, for B, there's a hydrogen there, N equals to 8, so it should be a non-net.
So is it the 2, 6, so it's the 2, 3's from A, so that's 6, 7, 8, and then plus 1 is 9. So
Yes.
it's not like directly attached. So it's not like
What do you mean directly attached? C is directly attached to B. A is directly attached to B.
I think I'm getting it mixed up with the oxidation states, where like that's like whatever's directly attached.
Yeah. Oxidation states has to be whatever is directly attached. Yeah.
Okay. Yeah, I understand this. Other than that, this exam was fine. Oh, and then I have another exam to show you. Just leave this here. Oh wait, this is a dumb question. Heptoxide, is that like an alkoxide?
Heptoxide.
Is
Where's the
an
name?
alkoxide?
Yeah, that's an alkoxide with 7 carbons, like the one you asked me on yesterday.
Okay, because for some reason my brain was blanking when I was going over this exam, and I was like, what is that? And I couldn't find it anywhere.
It's a strong base, obviously, but it's gonna be so large.
Oh, I'm sorry. It was this one that I had an issue with. This one. I didn't even know how to answer this. Like, I did it again today, and I was like, I don't know.
Is this the answer key?
Yeah.
For which one?
This one that says elimination. Because what I did is I joined these two together, so it's like...
No, that one will happen by Williamson ether synthesis. We talked about that, but that happens by SN2. SN2 does not happen on tertiary.
Tertiary. Okay. So... What is this, though? Like...
It's E2. The chicken foot always does E2. Stop sharing, I'll show you.
Because I don't know why I like blinked so bad on this question.
So, what was he asking for? The product or the type of reaction?
Just the major product. So it didn't say elimination. It was just those two. And
Okay.
then like an error.
So I see that I have bulky nucleophile, so it can never be a nucleophile. And then I have a hindered electrophile, so no SN2. Yet this would have been a strong base for E2. Would have been.
I did too. Is what I did.
Okay, strong nucleophile for SN2. SN2 will not happen because this is huge and is going to a tertiary. So instead of that, you want to show the beta hydrogen. That is what E2 does. This carbon is alpha, this is beta. Beta hydrogen elimination, just like this. You're going to get a double bond. And this is taking a hydrogen, so the other
That's an OH.
Thank you. And then you have the inorganic product.
Okay.
Screaming.
Really, I don't know why. And because I wasn't given any guidance on where to go, so I was like, what do you want?
Yeah. I stopped sharing again before this laptop.
I think that might be all I have for now.
Alright, so what you do, you keep studying like you are doing.
Yeah.
Screen 21, 2019, go back, screen the earlier ones, meet yourself in the middle.